way, and Dr. Asa Vidramar's Jake's his PhD journey. Jake got a bachelor's degree in theoretical and applied mechanics from the Science and Technology University of Science. No, the University of Science and Technology in China. It's a good place. During that period, he also spent a semester in the Netherlands working in a lab that dedicated himself to human engineering. Shortly after he finishes in 2015, he joined us for his PhD in 2016 at a time. And we started working on this project. This project was actually funded after Jake started by the Australian Research Council and involved both theoretical, numerical, and full-scale experimental testing. Jake has been a huge part of the design of the experimental setup and of the building of this full-scale testing facility. We'll see some pictures in his seminar presentation. I don't think that the pictures make justice to all the hard work put into the PhD, but you will see a glimpse of how this system looks like in reality. This is a quite unique project in which we were able to develop a scheme in numerical modeling, machine learning, artificial neural networks, and couple this to a full-scale experimental facility. Unfortunately, some of the results are coming just online. There was a test done yesterday, one more on Saturday. So not all of the data is going to be shown here, but that's the nature of doing the fieldwork. It's really cool, but it takes some time longer than we expect. Jeff has delivered a number of talks around the world in international conferences, representing the university and I quite well. And I expect that it's not going to be different this afternoon. Okay? So Jake, the floor is yours.
Thank you very much, Guillermo. And thank you for attending my seminar. My name is Zhou, and during the past 3.5 years, I've been working on the direct geothermal energy, reducing the rural industry's carbon footprint, under the kind supervision of Professor Nasulio over there, and Professor Lu Ai, and Dr. Big Marx, who's currently in the University of New South Wales. Okay, to begin with, let's have a look at the global energy consumption. In 2016, there's estimated to be 13,000 million tons of oil equivalent per year, which results in the greenhouse gas emission of over 50 gigatons of CO2 equivalent per year. And within this, this kind of consumption and greenhouse gas emission, about 50% of them come from space heating and cooling. Therefore, by improving the energy efficiency for the space heating and cooling, up to 1,500 million tons of oil equivalent of the global annual energy consumption can be reduced by 2015, according to IEA. And there are several approaches we can adopt to achieve this goal, including the improvement of the thermal performance of the building envelope, including determining the suitable operational schedule, as well as increasing the energy efficiency of heating, ventilation, and air conditioning systems. And direct geothermal energy can be used as a type of clean and renewable sources for highly efficient HVAC systems. When doing heating, the heat is extracted from ground into the building via ground source heat pumps, as well as ground heat exchangers. And when doing cooling, the reverse cycle will happen, which means that the heat will be injected into the ground via the ground heat exchangers and the ground source heat pumps. For those of you who's not very familiar with the HVAC systems, would typically use coefficient of performance, which is defined as a ratio of useful heating or cooling loads provided to the work required to estimate or as a measurement of the efficiency of the system. For example, for a well-designed ground source heat pump system, we can expect the COP to be larger than 4, which means to provide over 4 kilowatt hours of heating and cooling demand, we only need to consume 1 kilowatt hours of electricity. As a comparison, for air source heat pumps, we typically have the COP between 2.5 to 3.5, and for gas burners, would normally only have the efficiency of 85%, which is equivalent to 0.85 COP. So you could see that ground source heat pump is quite a state-of-art technology with very high efficiency. And now one area that ground source heat pumps can be applied is agriculture in Australia. And in Australia, the agriculture and oil adding on processing industry contributes to 12% of the gross domestic product. And within the poultry industry, over 600 million chickens are raised every year, which result in the estimated heating and cooling cost to be over 80 million Australian dollars per year. If you're looking at the pictures in your right, you could see there's an inside look of a poultry shed, which is located in the Peace Ridge, New South Wales, located 100 kilometers north of Sydney. And why we're going to use such kind of state-of-art technologies in the poultry industry? That is because currently there has been very limited work conducted for hybrid geothermal system with horizontal GHGs, especially under rural industrial conditions. There's also very limited work that's being conducted for the building energy efficiency of the poultry industry, and there's no full-scale instrumented application of hybrid geothermal system with horizontal ground heat exchangers for the rural industry. That's why in my research, I'm going to develop a hybrid geothermal system that is suitable for the rural or especially for the poultry industry in Australia. And in this research, we firstly developed building energy model, and then we do the system design, installation, instrumentation, and then simulation, model verification, and lastly, we did some multi-objective optimization. So corresponding to this, my presentation will be delivered into three parts. The first part would be the heating and cooling loads and energy efficiency for the poultry industry. And then we're going to talk about the hybrid geothermal system for the poultry shed, including design, construction, instrumentation, as well as numerical simulation. And last but not the least, we're going to do the multi-objective optimization of this hybrid geothermal system. So to begin with, for the heating and cooling loads, we're using a commercial software called Transys to do this simulation. There are quite a lot of simulation parameters we're considering, including the location and climate, building envelope, chicken growth and heat generation, as well as the operational schedule. We don't have time to go through all of this, but I could emphasize one thing is that for the chicken growth and heat generation, we could see that for a typical cycle, it usually takes about 7 to 8 weeks. And we could see that the chicken can generate a lot of heat, especially at the end of each batch. We could see that one chicken could generate about 15 watts of heat. This is quite a lot because we sometimes have 40,000 or 50,000 chickens in one shed. And now, after I'm using this software, we've got some result. So this is the heat and cooling load for one summer batch, which happens from the end of the mid-December to early February. The pictures in your left shows the indoor and outdoor temperature during this batch. We could see that at the beginning stage, we require quite a lot of heating. It's because at the beginning stage, the chicks are quite young and vulnerable. And then when it grows up, the required indoor temperature goes down and then it stables. If we're looking at the heating and cooling loads, then we could expect that at the beginning stage, even if in summer, you still require some heating because the required indoor temperature is quite high. And then, because the heat generated by the chickens is quite large, we can expect the increase in the cooling and decrease in heating. So at the beginning stage, the chickens are very young. If we follow the green line, this is heat generated by chicken. At the beginning stage, it's very young. It does not generate any heat. And then when it grows up, it generates quite a lot of heat. That's why we have a decrease in heating and increase in cooling. Now this is just one example for one batch. In my investigation, I have tried to use the same method to try different starting weeks in a year. Say for this batch, we start at week 51, but there are 52 weeks of the year. So if we repeat this process for 52 times, starting from different weeks of the year, we could get some different results. So what we do is that firstly, we have the hourly heating and cooling loads for one batch, which I just showed you. And we could do a sum up. Say for the heating loads, we just sum up all the heating loads, so we could have a total heating demand. And we sum up all the cooling loads as well, so we could have a total cooling demand. And then we repeat this process for 52 different starting weeks of the year. So we would have 50 heating demand for 52 different weeks, and we would have 52 different cooling demand for 52 different weeks in the year. And after we're having this, what we can do is, based on this loading, we could do some estimation of the heating and cooling, i.e. the operational cost for these 52 possible batches. And now this is the result. We could see that, as you can see previously, the cooling loads, especially in summer, is quite larger than the heating load. So you could expect, if you're starting a batch in summer, you could expect quite a lot of cooling than heating. And then if you are starting a batch in the middle of the year, you are expecting larger heating cost than the cooling cost. We could also see, if we're looking at the overall cost, we could also see that the most economical time for starting a batch would probably be the first half of the year. And now, if we're looking in detail the cooling and heating cost, the farm is currently using gas burners or LPG gas burners for heating, which is quite low efficiency, but they are using evaporative coolers for cooling, which is very high efficiency. That's why if we are trying to replace the HVAC system, we could not find a better HVAC system for cooling, but we can definitely replace the heating system, which is currently the gas burners, with ground source heat pumps. And that's what we do. We are trying to replace the gas heating to the ground source heat pump heating. And after this replacement, we can expect a significant decrease in the heating cost. And corresponding with this, we could also see that the most economical time to start a batch switched a little bit to your right. And now let's do some more tricks, some simple math. Say for a typical batch, in our case, it lasts for 7 weeks. In that case, we can accommodate 6 batches per year, and we allow the possible intervals for each batches to be 1 to 6 weeks. In that case, do some simple math, we could get some possible schedules over 1,000. This 1,000 is just 1,000 combinations of different starting weeks of the batch. And then we can analyze this distribution. If we are plotting the 1,000 cases this way, we could see that we have some average system average cost, something like this, in the middle, which is about $14,200 for both heating and cooling. But if we choose the minimum one, choose the optimized one, this is only 13,600. In that case, there is a cost saving of 4.2%. And if we are replacing it with ground source heat pump system for heating, then firstly, the cost can be reduced significantly. And at this time, if we continue to do the schedule optimization, it can be further reduced by 4.5%. And this is the optimized schedule if we are using the ground source heat pump heating system by starting at the 5th, 14th, 22nd, 30th, 38th, and 46th weeks of the year. In this time, by doing this, we could achieve the minimum cost. Now, as I just mentioned, they are currently using evaporative coolers for cooling. We cannot replace it by using any other HVAC system to make it more efficient. But there are still some approaches that we can adopt to reduce the cooling cost, which is by increasing the ventilation rate. Let's think about if because of the heat generated by the chickens are quite a lot, it is possible that when the outdoor temperature is only 15 degrees and the indoor temperature could be 25 degrees, something like that. In that case, if we increasing the ventilation rate by pushing more outdoor air into the building, we can actually reduce the cooling load. And this is the result. If we increase the standard ventilation rate by 50%, you could see some decrease over here. And if we increase it by 100%, so we have 200% of ventilation rate, there's a even significant decrease. One thing we need to consider is that when we do purging, when we do such kind of ventilation, we are expected to consume more electricity for the fan. That's why we also, when we're evaluating it, we also need to consider the electricity consumed by the fan. But even if we sum it up, we could still expect 5% reduction in cooling costs if we are increasing the ventilation rate by 50%, and about 10% decrease in the total cooling and ventilation costs if we're increasing it by 100%. Apart from that, the last but not least thing I've done for this part is to investigate the impact of the building envelope. Say if we are increasing the thickness of the wall, we can expect a decrease in heating, but a significant increase in cooling. So unfortunately, the impact of the building envelope is quite marginal, sometimes even to negative, because if we are considering the price of material for increasing the thickness. Apart from those results I just showed you, I have also did quite a lot of other case studies, but they are just generating similar results. So to draw the conclusion for this part, firstly, by switching from gas heating system to ground source heat pump system, up to 60% of heating cost and up to 20% of heating cooling cost can be saved, which is also depending on that price. Secondly, the ventilation strategy tends to be the second influencing factor. The total electricity cost reduction for the cooling and ventilation can be 5 to 10%. And thirdly, the operational schedule is the third most important influencing factor. About 2 to 4.5% of operational cost can be saved on average if the operational schedule is optimized. Finally, the building envelope has been proved to be the least impacting factor because it cannot reduce the heating and cooling load at the same time. Now, after we have investigated the heat and cooling load and energy efficiency for the poultry shed, what we're going to do is that we are going to develop a hybrid geothermal system for this poultry shed. So now let's move on to part 2 about the construction and simulation of hybrid geothermal systems. The picture over here is just a top view of the farm I just showed you. So this is the field for the ground heat exchanger, and this is exact poultry shed, which is going to be installed with ground source heat pump systems. If you take another look, so this is the horizontal heat exchangers under construction. And in total, we have about 4.8 kilometers of pipe inside this field, as well as in the pond. In total, these horizontal ground heat exchangers can provide about 80 kilowatt of the heating required. And now this is another drawing, shows that we have different groups. We have horizontal straight pipe, horizontal slinky pipe, and then slinky pipe, 3 groups, and some pond. So this is the video when it's under construction. We can see there's some dense slinky loops over here, very dense, and there's some extended slinky loops over here. And for the rest of the field, it is already backfilled. And this part should be the horizontal straight pipe. Now let's look at the different configurations in detail. So we have the horizontal straight pipe I just showed you. We have 4 straight pipes in one trench. And in our trench, we have 70 meters, 5 meters of length of the trench, and 300 meters of the pipe. For the horizontal slinky loops, it's the same density. So we have 75 meters of the trench and 300 meters of pipes inside one trench. And then this is a dense slinky loop. We have about 40 meters of length of trench, and then 300 meters of pipes inside the trench. You can see there's a conduit over here and something attached over there, and that's actually our temperature sensors. We have installed about 200 temperature sensors in the field. We normally install 2 temperature sensors in one place, and then thermal insulated. And now, as Guillermo just said, unfortunately, we have some recent data, but it's just finished yesterday. So for this presentation, we just have some test data happened in April. We could see that during this hour, if we are operating a system which is actually extracting heat from the ground, you can expect a decrease of the ground temperature. We have 10 sensors in total for this trench, and we could expect this kind of unified decrease. And if we just plot the average of the inlet outlet, it will look like this. Now with this data, what we have done is that we use this data to do some verification and also conducted numerical simulation for the ground heat exchangers and ground source heat pumps. So I have used 3 different numerical approaches, which includes the finite element modeling, computer model physics, transient simulation, and artificial neural networks. So let's first have a quick look at the finite element model in computer model physics. So this is a trench, cylinder trench I just showed you, and this is enlarged inlet and outlet, and this is a soil field. And by using this finite element model, we could do a detailed analysis of horizontal ground heat exchangers. We could investigate the impact of the rainfall on performance of horizontal ground heat exchangers. We could investigate the impact of trench separation distance, as well as doing a comparison between different configurations of horizontal ground heat exchangers. And this is just comparison data, verification data with the experimental result I just showed you. Apart from that, I have also conducted simulation in trances. We could see in trances there's ground source heat pump, there's ground heat exchangers. We also have the weather data and heating load file. By using this trances model, we could do comprehensive analysis of the ground source heat pump systems, including the prediction of the hourly COP of heat pumps and prediction of the hourly inlet and outlet temperatures of the ground heat exchangers, as well as the performance of the ground source heat pumps under different loading and climate conditions. Now, before we go to the simulation results for trances, let's have a look at the heating loading patterns, which is load files over here. As I just mentioned, there are 6 batches in a year, and for each batches, the heating is mostly required in the first 3 weeks, as we can see over here. So if we are starting batches at the beginning of the year, you are expecting a lower heating loads, and if you are starting it at the middle of the year, you are expecting a higher heating loads. And what we can also observe from this figure is that for most of the times the heating load is relatively low. We could see that even if the peak load is over 200 kilowatts, for most of the times it's probably lower than 100 kilowatts. So what we can do about that is that we can introduce a definition called shave factor, which is defined as the installed capacity of ground source heat pumps divided by the peak heating load. In our case, it's 208 kilowatt. In this case, say we have a shave factor of 50%, meaning that we're installing the capacity of the ground source heat pump of about 100 kilowatts. In that case, only 50% of the peaking load of the ground source heat pumps can still provide over 90% of the energy, while the rest of the energy can be supplied by the gas burners. Why we're doing that, that is because, as you've seen before, by using ground source heat pumps, we're going to do quite a lot of field work, which has quite a lot of capital investment cost, while for gas burners, it's very economical to install. And by doing this, we can actually form a hybrid system where we have ground source heat pumps connected to different ground loops, and we have gas burners in the quarter shed to top it up. And we're using transit to do the simulation with trenches. Now let's looking at the simulation result. Firstly, the transit simulation result matches with the console finite model result. And then, if we're looking at in detail, we could see that for a typical year, we have 6 different cycles, which is shown here. And for each cycle at the beginning stage, you are expecting a higher difference of continuous operation of the ground source heat pump. And this is a high difference between inlet and outlet temperature. And we can also do something about the hourly COP of the system. Say at the beginning of the year, we have some hourly COP over here, and then in the middle of the year, if we're starting a batch, we will see the hourly COP over here. We can see that over here, the COP is slightly larger than this one, and it's much uniform. That is because in June, when you're starting a batch over here, your ground source heat pumps is under continuous operation because the heating load is high. And if you're starting in January, because your heating load is not that high, so some of the heat pump may switching on, switching off. They're not under continuous operation, and that has an impact on the COP. So what we have done previously, I just showed you, is that we have the hourly COP for one heat pump, and then we take average because we have multiple heat pumps in the system. Then we could have the hourly COP for the whole ground source heat pump component within the hybrid system. And after doing that, let's us do an average because this is hourly COP. If we do it for annual, if we do it annual average, we could have annual average COP for the ground source heat pump component. And then based on this, if we are changing the shape factors, we could have the annual system COP for the ground source heat pump component on the different shape factors. And that is the result. Say we have 25% shape factors, meaning we install about 50% 50 kilowatt of the system, of the ground source heat pump system, and then 50%, 75%, and 100%. It is a little bit counterintuitive because when you're installing a high capacity of the system, the COP tends to decrease. That is because, as I just explained, when you are installing a higher capacity, or when the load is not that high, you could expect a partial loading of the heat pump, and when the heat pump is under partial loading, its efficiency could go down. Another observation we have got from this investigation is that if we are doing the same simulation for continuously 10 years, from the first year or even the second year, we could expect an exact same pattern, exact yearly same pattern. So here we show the results COP for the second year and the 10th year. They are exactly the same. This is slightly different from a vertical system, because typically if you install the ground heat exchangers in a vertical direction, even if you have the same load, yearly load, it will have some impact. The previous year's loading will have some impact on the second and third year. But one good thing we can get from this thing is that as long as we have a yearly repeating pattern, when we need to do 1 year simulation, and that can be representative for the whole cases. Now, apart from the transit and finite element model, I've also developed artificial neural networks using machine learning. So we have different layers: input layers, hidden layers, and output layers. For input layers, I'm just using 3 very simple input parameters. These are the heating loads, the cumulative heating loads, and outdoor temperature. And by using this thing, we input into heating layers, we can get the COP prediction. And we can also use the same input parameters to get inlet temperature and outlet temperature, which is the structure need to be slightly modified because this is time dependent. And by using these artificial neural networks, what I can get is that we can get a instant and robust analysis of ground source heat pump systems. This including the hourly COP of heat pumps with ground heat exchangers. And we can also get the hourly inlet and outlet temperature of horizontal ground heat exchangers. This feature is not currently available in any commercial software yet. And in this investigation, we have seen that we can get instant result with reasonably high accuracy, and it can be potentially applied much more generally. And now this is the result. So the x-axis is the transit simulated COP I just showed you, and the y-axis is AM predicted COP. We could see that for most of the result, it is within the error, within the 5% error range. And this distribution here also shows that for the majority of the cases, it's within the 5% error range. And if we're doing this for the inlet temperature, it's even better. And the outlet temperature is much better. We can see almost all the result is within the 5% error range. And the last thing for this part is that I have also conducted a computational time comparison. We could see that ANN is about 100 times faster than Transys, and Transys is about 100 times faster than FEM. Because computation times can be very important if we are going to do some optimization. For this part, I've also did a lot of other analysis over here, which shows quite consistent result. And based on this analysis, I have drawn some conclusions. The first one is the high shade factor in the hybrid system could result in a lower COP due to the partial loading of heat pumps. The second thing is that there is a yearly repeating pattern for the inlet and outlet temperatures of horizontal ground heat exchangers, as well as the heat pump COP. The last but not least is the ANN can do the prediction reasonably well in seconds, while a transit simulation could take hours and console simulation takes weeks. And now let's do some multi-objective optimization of this hybrid geothermal system. In my investigation, there are two different objective functions that I'm using. The first one is the life cycle cost in net present value for 40 years. The second one is a life cycle greenhouse gas emission for 40 years. Why we're using 40 years is because the ground source, the ground heat exchangers can normally last longer than 50 years. And we're also expecting that the shed, the poultry farm, to be there, existing there for longer than 40 years. For this hybrid system, where I'm doing the optimization, I have introduced another component, which is the solar photovoltaic. By using the solar PV, we can actually convert the solar energy into electricity, and using this electricity to provide the energy required by the ground source heat pumps. And by doing this, it can make this system much more energy efficient. And for the solar PV, there are 3 different solar PV scenarios for the electricity generation. The first thing is that the first scenario is that we have no solar electricity storage. It means that at the time the electricity is generated by the solar PV panel, if it cannot be consumed by the ground source heat pump system, it will be wasted. The second thing is that, as we can see, the farm is actually quite a large farm. We're assuming that even if some of the electricity cannot be consumed by the ground source heat pumps, there are still some equipment in the farm which can consume this electricity. And the third one is excess grid setting, because as you may know, that in Australia, if you're generating electricity from solar PV, you can sell it to the government at the contract price. And if you can do this grid setting, there's literally no electricity generated by the solar PV panels will be wasted. And now let's look at some the results for the first scenario, which is no storage. And for this no storage scenario, we could see that there's life cycle cost, there's life cycle greenhouse gas emission. This axis is the solar PV size, and this axis is the shade factor. The shape factor is for the ground source heat pump component, and this is for the solar PV component. We could see that for the first scenario, the solar PV size, the optimum one, the lowest life cycle cost happened with a relatively low solar PV size and a relatively low shape factor, about 20 to 30%. But if you are going to minimize the life cycle greenhouse gas emission, we could see a slight increase in the shape factor, but a significant increase in the solar PV size. If we're plotting this in a different way, there's the life cycle cost, and this is the life cycle greenhouse gas emission. We could see there's quite a lot of different points over here, and if we follow this line over here, this is that when we fix the solar PV size and change the shape factor, look at this line. So this line is that if we fix the shape factor and change the solar PV size. We can see there's a line over here, which is a Pareto optimal front of our problem. For those of you who's not very familiar, Pareto optimal front is a front line over here. Well, on this line, you cannot reduce one of the objectives, you cannot reduce the greenhouse gas emission without increase the life cycle cost. It's also the same thing over here. You cannot reduce the life cycle cost without increasing the greenhouse gas emission. So this Pareto optimal front solution is the optimized thing for our cases. And now, for the second scenario, if we are going to the farm offset, meaning that in the farm there are some equipment that can offset the consumption, we could see that if we're going to minimize life cycle cost, the required shape factor, optimized shape factor, is quite similar, 20 to 30%. However, there's a significant increase in the optimized solar PV size. If we're going to optimize greenhouse gas emission, it would be quite similar to the scenario one. It's asking for about 20 to 30% of shape factor, but quite large of the solar PV size. And we could do the same Pareto optimum front. It just looks slightly different. And for the third scenario, it would look like this. In both cost and greenhouse gas emission cases, it's asking for very large solar PV size, but about the same, let's say 20 to 30% of the shape factor. And if we're plotting out the Pareto optimum front, because both the cost and the emission are asking for the same side, so the Pareto optimum front is relatively small on this part. And now if we're plotting these three things together, the first one is no storage, and the second one is we have some offset from the farm. The last one is that we can sell the electricity to the grid. You can expect the Pareto optimum front goes down significantly. It means that in these cases, if you are increasing the utilization of the solar PV panels, you can expect the significantly reduction of greenhouse gas emission. However, if we're looking at the life cycle cost, the reduction is not that significant. But if you are comparing with this point, which is original gas heating system, we could see that the ground source heat pump, if you are using the ground source heat pumps, it can reduce the life cycle cost significantly. But for this section, I've also did a similar analysis for different locations and scenarios, and it generates quite similar results. And based on these results, I have some conclusions for this part. First one is the hybrid geothermal solar gas system can be more economical and environmentally friendly than original gas-only heating system. And secondly, is that shape factor can contribute more in the aspect of life cycle cost, and solar PV size is more important in life cycle greenhouse gas emission. The last one is that the shape factor between 20 to 35% is optimum for almost all the scenarios regarding both life cycle cost and greenhouse gas emissions. And during my PhD, I've had a few publications. I have other few publications that is in progress. And I would like to, in the end, I would like to warmly thank and appreciate my principal supervisor, Professor Masilio, for his kind and continuously guidance, caring, and patience. I would also like to thank my co-supervisor, Professor Lu Ai, and Dr. Bin Max for their helpful advice and suggestions for my PhD. And then I would like to thank Professor Kenisa Shoka from University of California, Berkeley, and Professor John McCartney from University of California, San Diego, Mr. Rian over there, Dr. Nicholas Makasis, Dr. Mihanova, Dr. Lu, Lyndon Jason Page, and Dr. Stuart Kors for their direct help toward my thesis. I would also like to thank the rest of the research team and ground source and industry partners, ground source systems, and Gold Associate, and as well as my family members and friends for all their support during my PhD. And in his end, we expect that geothermal energy can lead us a step closer to a renewable and sustainable future. Thank you very much.
Thank you very much, Jake. That was a very clear presentation. I listened to this twice already. We have time for questions from the audience, if there is any. Yes.
I'm just wondering about, you said that you could sell back the energy to the PV. What was the sellback rate?
Yeah, the sellback rate is depending on the states. For example, in Victoria, would be about 10 cents per kilowatt hour of the electricity. Thank you.
In relation to the last set of results that you showed, you showed 40% shape factor, so 30% of the heating and cooling, sorry, the heating only provided by the heat pump. And also you want to optimize greenhouse gas emission. Basically, you need to have a solar PV system of 250 square meters.
Yeah.
All of this is per shed. All of the numbers are per shed of 40,000 chicken, okay?
Yeah.
And I couldn't see a scale. So if you want to install, if the farmers want to install 250 square meters of PV panels, do they fit in the roof of the sheds?
Yes, because for the shed it's quite large. For the shed it has about 80 meters of width and about 120 meters of the length. So even if half of the roof is fitting with solar PV panels, it can be fitted perfectly.
Any other questions?
Jake, sorry. You told that in your finite element modeling console, you consider the rainfall and some other ambient effects. So I want to know how did you do that?
Yeah, the rainfall, basically the rainfall is impacting the moisture of the soil, and then the moisture of the soil is impacting the thermal conductivity. So I and my previous student, master student, have developed something, had to do some little study, and we found some equations that could link this together. So what we're actually doing is that we're changing the thermal conductivity of the ground.
Oh, thermal conductivity.
It looks like by using geothermal heat pumps, there is significant savings on the life cycle cost of the operation of the chicken farm. Why is it that there is only one example in Australia, the one that you showed here? Why is the uptake so low?
Yeah, that is mainly because that even if there's a huge life cycle cost, the investment cost, the capital investment will be quite large. And for the farmers, some of them cannot find enough finance or justification to do this, to invest that amount of money at the first few years and expecting to return in 40 years or something.
Okay, do we have any more questions? If not, then please join me in thanking Jake for such a clear presentation and impressive piece of work. Okay?
Thank you.